I'm happy to have Andreas Thom from Dresden with us. And after we heard so much about stability in permutation, the last 3 weeks for this semester will be about stability in the unitary groups. In the next semester, we'll do both. We'll go back to permutation, but we'll also do more unitary groups. Anyway, today, Andreas will talk on stability, cohomology, vanishing, and non-approximate groups.
Yeah, thank you very much for the invitation. And yeah, I'm really happy to give this talk. And I see that it's really a mixed audience of people that are like experts in the field and others which are maybe more outsiders. So I hope I will give an interesting talk for all of you. And in any case, just interrupt me if there are questions. I think that's probably the best way to give feedback. I mean, I'm really missing giving live lectures where you can see the faces and can see whether they are bored or puzzled, and then you can adjust your lecture. But like this, I don't have this kind of feedback, so it's maybe good to interrupt me from time to time. Right. So this is the overview of the talk. I will first recall or maybe introduce some notions. Probably you have seen that already in the lectures that you heard over the last weeks about various approximation properties for groups. Then I will say a word about why this is actually interesting. So what are the applications of these approximation properties? And then I will discuss these issues of stability and non-stability and give you a cohomology criterion that implies in a certain situation that groups are non-approximable or are stable, and for that reason then in fact non-approximable by some additional argument. Okay. I have to say, I mean, maybe it's really good if you interrupt me from time to time, because last time I gave a talk in Texas, I think, and after 20 minutes, the connection was lost, and I was talking for 10 more minutes without noticing that there was nobody listening anymore. So maybe it's really nice if you give me some feedback from time to time, then I know that you are still listening. Okay, so let me start. I will speak about these finitary approximation properties of groups. And so in the very general setting, you start with curly C, which is a class of finite or compact groups. So maybe you have thought about the symmetric groups for a little bit in the last lectures. So more abstractly, you just assume that it has a metric which is invariant on both sides. So it's invariant by left multiplication and by right multiplication, and we call that a bi-invariant metric. And bi-invariant metrics are, I mean, exist, but many metrics that you know from geometric group theory, like word metrics, for example, or also from Riemannian geometry, from non-compact Lie groups, they will only be invariant on one side. So it's really a restriction that we are putting on the metric, which is more restrictive than you may think in the beginning. But for example, there we will see a few examples, and you have seen the Hamming metric, for example, on the symmetric group. And we say that the group is approximable by this class of groups if basically any finite piece of the group, it can be approximated up to some little error in the metric to an arbitrary precision by elements inside one of the groups in your family, right? And so more abstractly, this means that for any finite subset S and for any epsilon, you can map S to a group which lies in your family, so in the group, in the family C. And then on that set S, so whenever GH and GH are in the set, you have that this is actually almost multiplicative. So it's multiplicative up to a mistake which is smaller than epsilon. And on the other side, you also want that if you have a non-trivial element, then this is not mapped to the neutral element, which would not be very interesting, right? And for the first condition, I mean, only the first condition, we have a name. if something satisfies the first condition, we call that an S epsilon homomorphism, right? So it's not quite a homomorphism, but on the set S up to a mistake of epsilon, it is a homomorphism. And to those of you that have seen these kind of definitions, for us, it's not very important whether we make a definition where you have 1/2 here, or you have some constant depending on G, or you have something else. So that's in most of the interesting applications, this really doesn't make a big difference. And we just write 1/2 here. So it should not be, I mean, there should be a lower bound somehow that is independent of S and epsilon. That's the point. Okay, so that's the definition. I guess you have seen that before. And we will now talk about 3 basically families of finite compact, compact metric groups, in fact. And it will always be the same group. It will always be UN, the unitary group on an n-dimensional complex Hilbert space. And then there are 3 natural norms that you can consider on, I mean, there are many more norms that you can consider on n by n matrices, but there are 3 norms that we will consider. And one is what we will call the Hilbert-Schmidt norm. And I mean, it's the normalized version, right, where you divide by n in order, right, to get that the identity has Hilbert-Schmidt norm equal to 1. Then there is the Frobenius norm that right, is almost the same, only that it has a different normalization. And then there's also the operator norm, which is just the largest square root of the largest singular value of your operator. Right, it's another very natural norm. And we will consider these 3 families. And so each time you get a different approximation property, right? So you can imagine that it depends a lot on how you define the metrics on UN, whether a group is approximable or not, right? And it's even if one metric is bounding another metric, I mean, one norm is bounding another norm, it's not clear how these approximation properties behave, because if I go back here, then you note that there are inequalities going in both directions. So something has to be smaller than epsilon and the other thing has to be bigger than 1/2. So that means that even if something is approximable with respect to one norm, it doesn't mean if that norm bounds another norm that it's also approximable with respect to this other norm, right? So it's really 3 a priori completely independent properties that you obtain. And they have come up, at least the first and the third have come up in the operator algebra community. So the first one was in some form discussed by Alan Kohn. And
I have a question, 2 questions.
Yes,
one, when you say that it has this embeddable property, it's all epsilon, you can do it, or?
Yes. So
okay.
Let's go back to the definition. Sorry, I have to go back
okay.
here.
I just wanted to clarify that. Yeah, so that's
right.
2.
So I'm saying for any, and that refers to, I mean, I could say for all finite subsets and all epsilon. Maybe that would be more precise. Yes.
And the second question, usually, like in the Baum's-Kohn conjecture, there's some definition that's useful for a group, because then it allows you to say something interesting say in topology. Why does Kohn make this definition?
Well, we can say something interesting in topology, and I will come to that, but that was not the reason why Kohn made this definition. So Kohn, he basically observed that this definition is satisfied for the free group and for all kind of groups that he could imagine, residually finite groups and so on. And in a side remark, he said that this ought to be true for all groups, or in fact for all type 2-1 for Neumann algebras. So it was just basically...
You will give an application that if this property is true, then something's interesting.
Yeah, I will give you a very interesting application. If you are interested in topology, then this will really be very, very concrete.
Okay, thanks.
Okay, so you have this Kohn embeddability. That's the first one. Then the second one, this is what we call Frobenius approximable. And the third one, this is sometimes called MF. Also, it's a notation from operator algebras, relating to matricial finiteness. That's what it abbreviates. So, okay, so these properties, at least the first and the third one, have been studied in operator algebras, and the second one is the one that we introduced in a paper with Alex Lubotsky and Markus de Chiffre and Lev Klebsky, basically because we could say something non-trivial about this approximation property, right? So we will come to that at the end of the talk. And so there are various questions. So Con's question, that's from 78. This was asking whether all groups are Con-embeddable. There are also Kirchberg in some form asked the question whether all groups are MF. That's not really published, this conjecture, but he made this conjecture on Oberwolfach on various occasions. But as I say, there are no implications between the two questions. Okay. Right, so let me give you some examples of Con-embeddable groups, right? So residually finite groups, so they have all the approximation properties that you can think of, because it just works with epsilon equal to 0, right? You can just let the finite group act on its left regular representation. This gives you a homomorphism into a finite dimensional unitary group. Epsilon is 0. Everything is actually a homomorphism. Amenable groups, that's also a class of Con-embeddable groups, because essentially this Fellner set allows you to define an almost unitary representation on L2 of the Fellner set, right? That's something that is really a fundamental construction of examples of Con-embeddable groups. If you have seen Sophic groups, they are Con-embeddable because permutations are unitary matrices. And then this whole class of Con-embeddable groups is closed under various constructions, inverse and direct limits, certain types of products, even with amalgamation, and also certain extensions. So there's ongoing work on proving more and more permanence properties for these classes of groups. But so far, we are still far away from proving maybe all groups are Con-embeddable. In fact, in the recent, this year and beginning of this year, there was a counterexample to Con's embedding conjecture, which is slightly more general. And maybe this will also lead to a group which is not Con-embeddable, but at the moment, this is also not clear. Okay, so if you want to think of it in more concrete terms, so what does it actually mean to be approximable? And
all right, can you clarify that last comment? Is this computer science connection that you're talking about? That?
Oh yeah, exactly. So this was connection with quantum information theory and the Zirilson problem in quantum mechanics, right? And from that side, there was a completely new approach to the Con-embedding problem. But the Con-embedding problem, yeah, right, it is a problem about 2 1 factors in general, and they do not all come from groups. And the counterexample so far, if the proof holds, is that it's only a 2 1 factor. It doesn't necessarily come from a group. So that's the missing piece.
You see, I've been asked by computer scientists why that's interesting. That's why I'm asking you this question. Why
right, so we will come to that.
Okay. Thanks.
So,
Peter, in the second semester, I think I will organize also part of the seminar, some talks that will describe a little bit of this connection.
Yes.
Just understand, I'm responding to your request to interact.
Yeah, it's excellent. Yeah. So every 5 minutes, I know that you are all still here. That's very good. So let gamma be a finitely presented group. So that's finite set of generators, finite set of relations. Then another way of saying that a group is approximable is to say that you find homomorphisms from the free group on the generating set, so that the relations that you want to hold exactly in gamma are only holding up to epsilon in with respect to the metric, right? So that's like a slightly different form of saying exactly the same thing. So it's not complicated to see. that such a group here is con-embeddable or approximable with respect to some family that I have introduced, exactly when there are sufficiently many maps from the free group to the corresponding unitary groups, which are better and better homomorphisms. And now the injectivity is expressed in a slightly different form. You say that for an element which is not in the normal closure of the relations, so an element that will be non-trivial in representing an element which is non-trivial in gamma, then you want, an element which is non-trivial, you want that this sequence, oh, sorry, this is exactly the wrong thing, is not close, to the identity matrix as n tends to infinity. Right, so this is exactly saying that that it's kind of still detecting all the non-trivial elements in your group gamma, right? So it's not complicated to see that these two things, this con approximation and the properties that I have discussed in this proposition, are equivalent. And so this gives us an interesting, I mean, kind of like conceptual relation with objects that come up in model theory in a very natural way, but they're also quite useful. Well, certainly in functional analysis, they are quite useful just to conceptualize some approximation properties. So if you have an ultra filter U and you have a family of metric groups, then we can define a metric ultra product. And that's essentially, I mean, the notation is this. And by definition, it is the product modulo a normal subgroup, which is defined as follows. It's given by those elements that converge to the identity along the ultra filter with respect to the metrics on these individual groups. And it's from the triangle inequality, this is a subgroup. And from the by invariance of the metric, this is a normal subgroup, so you can divide it out. So that's, for example, where you see clearly that this by invariance is a natural property to have. So now I can give you a third way of saying that a group is approximable. If a group is approximable by C, by a class C, then it happens if and only if it embeds into a metric ultra product of groups from C. Right, and so that's a very natural question now. So if you take C to be maybe all the compact metric groups or all the finite metric groups or all the symmetric groups with arbitrary metrics, each time you get another approximation property. And in the end, it will boil down to a very natural question about embeddability in an ultra product of such groups. Right, so a very weakest form of all these approximation properties is the following question. So since all these groups are compact, you always have that this product here that comes up is itself a compact group. So you could ask, so that's a question that I like very much. Sorry, it's a question that I like very much. Is it true, or do all groups gamma embed into a quotient of a compact group? Right, so that's maybe the weakest form of all these approximation properties and would be very nice. So maybe that's actually wrong, right? So nobody knows. So I really like this question. Okay, but now we come to why do we actually approximate? So why is it helpful? And I think you are probably convinced that approximation by finite groups, for example, is very useful, right? So for example, as soon as you have mapped your problem into a finite group, you can use just exhaustion, just algorithms that would enumerate all the cases and would solve some problems. So for example, the word problem for a residually finite group is solvable, right? So these type of things are just useful in order to understand the group. And there's a problem that I would like to discuss, which has a positive answer for all the groups that are embeddable, and I want to explain you how that goes. So the following definition: let gamma be a group, and then you have constants in the group, and then you have some natural numbers, integers, and then you consider the following equation. So this equation has one variable that's called t, and it's of the form g1 t to the epsilon 1, g2 t to the epsilon 2, and so on. So it's like some sort of a polynomial equation, but in a group you only have one type of operation, so it's not involving multiplication and addition, it's just involving multiplication in the group. And we say that such an equation has a solution in the group gamma if there exists an element in the group that solves the equation, right? And what does that mean? You just plug in h for t and you compute and you get the solution, right? And that's a very easy, very natural, situation that you can consider. So most of the time, of course, the solution will not exist, right? So most equations do not have a solution in gamma, but it's very natural to wonder whether one can just find a solution in a group maybe which is slightly bigger than gamma. Maybe we say that an equation has a solution over the group gamma if there exists a group that contains gamma and also contains a solution to the equation, right? But just considering the equation as an equation in the bigger group. And that's something very natural that one can do, and it's very successful, as you know, for example, for fields, right? If you have a field, a polynomial equation is not always solvable, but certainly it's solvable in a field extension, right? At least in characteristic 0. So you can wonder, is the same true for groups? And let's look at the number of examples. And so the first example is the following. So you have two elements A and B, so these are the constants, and you look at the equation which is of this form. So what happens if you can solve this equation? Well, then you find an element, call it T, so that A inverse will now be conjugate to B, right? And that's a very strong condition because it implies that A and B, that they have the same order, right? And that was not part of the assumption, right? So if the group contains different types of torsion, then you have a problem, right? Then you cannot solve equations even if you extend your group to a bigger group. And then there's a second example that's even more striking in a way, which tells you that even in this particular group, which only has one type of torsion, only p torsion, you can write down an equation which is not solvable. And well, why is it not solvable? So the argument, you can see it already. So what would it mean that you can solve it? It would mean that a square is conjugate to a, and it's conjugate by an element that is also conjugate to a, right? So this element which conjugates a to a square is also conjugate to a. And so that's a problem because conjugation of a to a square, that's just multiplication by 2, and multiplication by 2 on Z mod P does not have an order which is, does have an order which is dividing P minus 1, and in particular it's co-prime to P. So this automorphism that's implementing the conjugation, it cannot itself have order P, right? And so you get a contradiction. So just one type of torsion is enough to create problems. And so you may think, maybe you think two things have been a little bit strange. First of all, there was torsion, so maybe you need torsion freeness. And the other thing that maybe has been observed by some of you is that the sum of exponents here is equal to 0. So the sum of exponents is 0. In the other case, it's also equal to 0. So maybe that's a little bit special this case. So maybe if you have the exponent sum not being equal to 0, maybe that's easier. And indeed, there is, let's make the following definition. So let's call an equation non-singular if the sum of exponents is not equal to 0. And then there is a conjecture by Cavere, was also made by Laudenbach in the 60s, is that for any group and for any equation, if it is non-singular, then it has a solution over the group gamma. There's also the conjecture that no matter what equation you take, if the group is torsion-free, then you have always a solution. And the only real progress in that direction and that generality was by Anton Klyatko, who proved that if the group is torsion-free and the equation is non-singular, then this equation can be solved over the group gamma. Okay, so that's the progress so far.
Excuse me?
Yes?
I have a question. What is it about this non-singularity that makes it easier? Like we saw some examples, but is there an intuitive reason as to why it should?
Well, I mean, we will see one way of proving the Cavere conjecture, and in that proof you will see how it is very useful to have a non-singular equation. But apart from this, we don't have we don't have a counterexample, and right. So I mean, but let me give you this.
What is Andreas? What is the funny property of spheres in the title of the paper? What's the funny?
Well, that refers to the. I mean, this is a fantastic paper. It's a typewriter manuscript, and it's was published in this form, and it's a topological property of the two-dimensional sphere that was used in the proof because it was related to Van Kampen diagrams, and then there was some like geometric combinatorics done on the sphere in order to prove this. Really a nice proof. It was very hard to read in the beginning. So let me just quickly say, why is this actually complicated? Right, so why don't we just do the following? We take a free product with a new variable and we divide out the normal subgroup generated by the relation. And here you go, you have a group which contains a solution. But the problem is that nobody tells you that this is an injective homomorphism. So it might be that for some strange reason, the normal subgroup that is generated is so big that it contains elements of gamma itself, right? And yeah, that's very hard to rule out. And this is really a conjecture. I mean, originally came up in low-dimensional topology in the surgery on knot complements. And so it has a concrete meaning. So there was the notion of something being pi1 injective. So that would exactly refer to the injectivity of this homomorphism in this situation, right? So that's the relationship. And so now let me give you the positive result. And in some sense, it says that the group UN, the unitary group, that this is algebraically closed, because the theorem of Gerstenhaber and Rothaus exactly says that if you have a non-singular equation in UN, then it can be actually solved in UN, right? So it's a little bit like the complex numbers. If you embed a field into the complex numbers, then you can give a topological argument that you can create this field extension by just finding a topological proof of the fundamental theorem of algebra and then adding the solution to your field. And it's a little bit similar here, only that we have to argue in a slightly more sophisticated way. So consider our equation, the equation that we want to solve, now as a map from UN to UN, right? So plug in an element in UN and just compute. And what you want to obtain is the neutral element as an image, right? Then you have a solution. And so we study this as a continuous map. And since the unitary group is connected, all these constants GI, you can move them continuously to the identity matrix, and you can simplify this map a lot. It's now just given by raising t to a certain power, which is the sum of these exponents. And now the non-singularity, of course, helps you, because this is now not the trivial map, but it's a map which is highly non-trivial. It has a non-trivial topological degree as a map between topological manifolds. And that's also very easy to see. So this was computed by Hopf. But it's very easy to see count the number of generic pre-images of a matrix. So if you raise it to some power, to the dth power, then there are exactly d to the n generic pre-images, so the degree is non-zero. And the map, in fact, must be surjective for that reason. And so in particular, since also the degree is a homotopy invariant, you conclude that also this map must have been surjective, the map you started with, and hence there is a solution. So that's really a fantastic argument, I think, because it's, well, first of all, solves the problem, and secondly, doesn't tell you where is the solution, right? So it's very hard, right, to use it for practical purposes, even if you have a concrete finite cube and a concrete equation. How do you find the solution, right? It's just an existence result, like Power's fixed point theorem. So it would not give you a concrete measure of how complicated this solution is, for example, in algebraic terms. Right, but it has a nice consequence. Well, it says that a non-singular equation with coefficients in a finite cube can now be solved over the finite cube. In fact, it's not complicated to see that a finite extension of the cube is also enough, right? Just by residual finiteness of linear cubes, you can just move everything back down to a finite cube. And if you think about it a little bit, then it's then you see that the same holds for residually finite cubes, right? So you could just embed your cube into a product of unitary cubes, for example, and solve in each of the factors and so on. And that gives you that a residually finite cube also has this property that all the equations can be solved in some cube extension, namely this product of unitary cubes. And now Vladimir Pestov, in writing a survey about hyperlinear cubes, observed that in fact the same argument, exactly the same argument, also applies to these Cohn-embeddable cubes, because they are a Cohn-embeddable cube is a cube which embeds into a product of unitary cubes divided out by some normal subgroup. And it's very easy to see that this.
So this is true also for the other, like for Venus operator. It doesn't matter
yeah. So it's also true for Frobenius approximated or for MF cubes, but I'm just stating it for Cohn-embeddable because that's the, I mean, potentially largest class. But you are right; it's true for all the other properties as well.
And this answers my question. Thank you.
Yeah. Okay.
That's
nice.
a good example.
Right. Okay. So I have prepared, I mean, I have to see that how I'm doing with time. So I have prepared some results also for the many variable case for the systems of equations over cubes, and I will go up.
You remember, Andreas, that we are going for 75 minutes, not 60.
Oh, okay. Well, that's good. That's good that you say it now. Okay, well then I can spend a few more minutes maybe on these equations with many variables. So remember an equation, the one equation was just an element in the free product of, well, a copy of Z and the group G itself. It's just a formal expression in terms of T and constants from the group G. So now in general, what you naturally would like to study is K equations in N variables. And that's naturally just K elements of the free product of Fn and G. And now we have to talk about this non-singularity condition. And the non-singularity was made in such a way that it didn't involve the constants anymore. So you were just forgetting all the constants and just remembering basically the words that you were obtaining by setting these constants equal to the neutral element. And that's these K elements from the free group on N generators. This is just the image of W1 through WK under the natural augmentation homomorphism that maps G to the neutral element. And so the natural question is, under what conditions on these elements that you see here is the homomorphism phi injective? And that's exactly equivalent to asking when can the equations be solved simultaneously in a group containing G. So that's in some sense very fundamental problem in group theory. And the algebraic topological version of it is the following. You have an embedding of CW complexes with the quotient two-dimensional. Under what conditions is the homomorphism pi1 injective? Right, well, that's also a very natural question. And the conjecture that we made with Anton Klatschko in a paper was that as soon as the equation is non-singular in the sense that if you apply the augmentation to W, you don't get the trivial element, then you should be able to solve the equation even if it contains more variables, right? And that's already a non-trivial extension. For example, this W epsilon of W, it could be A, B, A inverse, B inverse, for example, and then you cannot reduce it to the one variable case, even though it's just one equation. And what we proved back then was that this holds if this epsilon is not too deep in the lower central series. So if it is not contained in in the third step of the lower central series. And so in fact, so a few years later, we could prove this in general and even generalized it. And that's now the following theorem that I want to just mention. It's a result with Martin Nietzsche from 1-2 years ago. And it's using, in the end, the same scheme as Gerstenhaber's and Pestov's observation. So in the end, it works for all con-embeddable groups because you can reduce the problem to unitary groups in this situation. And for the unitary groups, we use some sort of topological argument. And the condition that we need is the following. So this is your so you consider the presentation complex of the presentation of the naturally associated group. And what we need is that this presentation two complex admits a covering with trivial second homology. Right. So why does that imply the conjecture up here? This conjecture, well, it implies it because a one-relator group always has, so for example, if it's torsion-free, then the universal covering has a trivial second homology, right? So, and in general, that's a condition on a system of equations, but it seems to be exactly, it seems to be actually an if and only if condition, but we were not able to prove that. But it's giving another application of this class of con-embeddable groups. So there are a number of conditions that imply this the existence of this covering with trivial second homology. And right,
Andreas, can you say a word why this triviality of the second homology is relevant to the problem, where it really comes to play a role?
Well, it comes for us. It helps to find the solution to this a solution to the system of equation because it controls that a certain map between products of unitary groups that naturally comes up has a non-trivial degree. So it's following the same route, but I cannot say it more precisely. I mean, it's comes up in the proof. But it's a property that has been studied before for presentation two complexes. So there's the notion of a Cockcroft complex, and so the in the study of two complexes, it's a condition that comes up naturally. For example, also in Whitehead's conjecture, right, on acyclicity of two complexes. Well, if it's acyclic, for example, it also has a covering which has trivial second homology. So there are a few cases where this condition is satisfied. And maybe let me just speak about the second one, which is a little bit surprising, at least it was surprising to me. And that's simply the case when the presentation 2 complex is aspherical, meaning that the universal covering is contractible, right? And this is an interesting case because this happens even if the number of equations is much, much larger than the number of variables. So for example, in these random presentations, you typically have like growing number of relations, but a finite number of variables. And still the presentation 2 complex is aspherical. That means, and that's really surprising because in the like polynomial world, we are used to the fact that you can have at most as many equations as variables if you want to solve them simultaneously in great generality. But here, apparently, you can have many more equations than variables as long as they are sufficiently complex using the non-commutativity of the group multiplication in a very subtle way. Okay. Okay, so I'm now coming to the stability, so the actual topic of the semester. And I think you have seen that definition also because you talked about stability in permutations already, but let me repeat it. We say that the group G is called C-stable, and I'm always thinking about G as being concretely given in terms of a presentation and finite presentation. And now it's an epsilon delta definition. If for all epsilon, there exists a delta, so that if you have a delta homomorphism from G to a group which is in your class, then it is epsilon close to a homomorphism. And remember this delta homomorphism, this was saying that, that the relations are mapped less than delta to something less than, a distance less than delta to the neutral element. And epsilon close means epsilon close on the generating set, right? So epsilon close, this means that the maximum over x in x of the distance of phi x, psi x is less than epsilon, right? So that's just the distance on the generators of these homomorphisms. Okay, so it's kind of very natural. And there's a lot of work recently on stability in various contexts. So in, for example, in the norm, operator norm context, also in the con-embeddable context. And so what I want to discuss is this Frobenius situation, because there we can establish an interesting relationship with some interesting homological properties or analytic properties of groups that we have examined. So we will speak about a Frobenius stable group if it is stable with respect to the family of unitary groups with the Frobenius metric. Okay. And now there are 2 basic examples that I would like to mention. And one is the group Z squared, so a very easy group. And the other one is this Baumschlag-Solitaire group 2, 3, which is generated by 2 elements. One is conjugating the square of the other onto the cube of it, right? So that's this relation that defines the Baumschlag-Solitaire group. And I claim these groups both are not Frobenius stable. And this result for Z squared, that's essentially due to Voiculescu. At least he has, I guess, was the first to write it down explicitly. And it's very easy. You take 2 matrices. One has, let's say, e to the I psi, e to the 2i psi, e to the 3i psi, and so on the diagonal. And the matrix B is just, it has zeros on the diagonal and just shifts everything down. So these are 2 unitary matrices. They are both far away from the identity. But still, if you compute the commutator of A and B, then you will just obtain e to the I psi times the identity matrix. So this is if psi is, for example, let's say an nth root of unity, which is very close to the identity, to the complex number 1, then this matrix will be very close to the identity matrix, right? And still, it seems quite like plausible that there will be no matrices which are near A and B, which will be actually commuting with one another. So that was the first example of this type of phenomenon that was, I mean, at least explicitly noted, of matrices that almost commute, unitary matrices, but they're not quite commuting, right? And of course, in order to prove that that they are not really close to really commuting matrices, one has to come up with a clever argument. But so well, it's again some sort of a degree argument that helps you in this situation. The group BS23 is also not Frobenius approximable and Frobenius stable, sorry. But that's due to a different type of reasoning, because we know that this BS23, so BS23, this was this group AB square is equal to B cube A. This is not residually finite, because one can check that in any finite quotient, the commutator of A and this conjugate of A will be the neutral element. That's due to so it's not a very long computation in just using that the order of A must be finite. The order of oh, sorry, I mixed it up. It's the other way around. So it's B and it's A, B, A inverse. So any finite quotient, this is trivial, but in the group itself, it is a non-trivial element, as one can see. And now what happens is it's really an interesting construction. One can write down a concrete epsilon representation of this group, where this particular element is a non-trivial element, and it's very far from the identity. And just because of this fact, you know that there cannot be any homomorphism nearby, because for a true homomorphism, it would have to be trivial, right? And since it's far away from the identity, it proves that this epsilon representation cannot be close to an actual representation. So that's a very, very short explanation of why this group is not Frobenius stable. And well, in fact, I would expect that most of the groups are actually not Frobenius stable, because it's a strong condition, but right, we don't know. We were actually quite happy to find a class of groups which actually is Frobenius stable. And that's now the interesting connection to cohomology with Hilbert space coefficients. And that's the following theorem, which is joint work with Markus de Chiffre. He was a PhD student in Dresden. He's now doing 3D printing, Lev Glebsky and Alex. And the statement is the following: we prove that the group G is Frobenius stable if it is what we call 2 Kazhdan. And 2 Kazhdan is a condition which is defined to be the following. You want that the second cohomology of the group gamma with coefficients in all the unitary representations is equal to 0. So why do we call it 2 Kazhdan? Well, Kazhdan, the property T, Kazhdan's property T is equivalent, at least for countable groups, to having the first cohomology of G with arbitrary unitary coefficients vanishing. And now we are asking for the second to vanish. Right, so, okay. That's our theorem, right? And now, of course, the question is, can we use it for something? And a corollary to it is that there exists a group which is not approximable in this Frobenius family of groups. So it's not Frobenius approximable. And what's the argument? So the argument in one part is very formal. It just says that, well, first of all, if it is Frobenius approximable and at the same time Frobenius stable, then you can combine the two properties, and one gives you the existence of an epsilon homomorphism, and the other one gives you that the epsilon homomorphism is actually close to a true homomorphism. So you conclude that you have actual homomorphisms to unitary groups, and because everything is finitely generated, you conclude that the group is actually residually finite. So this is a useful observation. And what we now have to come up with is a group that satisfies the conditions of the theorem. So it has two Kashdan, and at the same time is not residually finite. And the only groups that we knew were two Kashdan. Sorry, yes?
By the way, I mean, one of the useful things about Kashdan is that it's true for a group if and only if it's true for any lattice inside. I mean, is that formal and works for higher analogs of Kashdan?
We don't know. No, I think it's, so Kashdan's property T has various different descriptions, and some of them are, I mean, work well by going to an ambient Lie group and restricting back to a lattice, but it's not so easy in this situation. For the second cohomology, we don't know. Right, I will come to this. I mean, I will come to a question which shows you that we know, in fact, very little about, which is this question. Right, so SL4Z, is it 2 Kashdan? That's an open problem as far as I know. But let me first finish the proof.
Why do you say SL4? You know, for SL3?
Well, I don't know for SL3, in fact, but I would not expect it to be 2 Kashdan because it's just, the rank is just 2.
Oh, the homology. Yeah, you're right. Maybe the second.
No, he expects it for SL5.
You're right, yeah.
But to Shmuel's question, what about SL4R?
I think there is definitely work for, I mean, I don't know, I don't have a precise answer, but there is a lot of work on vanishing up to the rank -1 and so on. But sometimes there are special conditions on the unitary representation. So maybe they are tempered, or maybe there's some addition, maybe it's in an analytic setting or so, but I don't know in this generality that I have written it, I don't know if it's known for SL4R or 5R.
But just back to his question. So can you state your Kash2 property, whatever you call it, 2 Kashdan property in terms of in the case of a semi-simple Lie group, can you state it in terms of the unitary or the representation theory of the group? Well, unitary, I guess.
Well,
it is said. It is said because it's just the vanishing of the cohomology. That's what we call Kashdan, not the stability. What you are meaning? Can we say stability in terms of the group? That's not clear, though.
Well, I think for SL4R or 5R, I think probably there's enough known to answer this question. I mean, there's also a question about reduced and non-reduced cohomology and about tempered and general unitary representations.
I'm just saying that one knows so much about those for semi-simple groups that maybe is it a question about some representations being isolated in the unitary dual or not?
No, I don't think this is related. No.
All right.
Yeah. But there are various problems. So it's really an arbitrary unitary representation. So it's not an irreducible one, and so on. So you have to really prove.
Is it admissible?
No condition.
Okay. All right.
Yeah.
By the way, there is a beautiful, just because I don't think it's so well known, there's a beautiful paper of Vaughan, which identifies all the isolated representations, the cohomological ones for semi-simple groups.
Right.
In other words, generalization of Kashdan to all.
Mm-hmm.
in the Feld topology. Yeah.
And let me just say that the Shapiro lemmas here, which is usually the standard thing to relate cohomology of a group and an overgroup, is sometimes delicate when you go from a lattice to the full group.
Yeah, so this would be a non-co-compact lattice. So I think there are various problems, but still it seems a very reasonable question. I mean, probably it's true for SL4R. And
is that a problem
also,
because of?
Yeah.
I was just going to ask Alex's comment about Shapiro lemma. Is that because of closure issues when taking Ds, or is it a different point?
Well, I think, yeah, I mean, I think it works better for the reduced cohomology, first of all. And then I think there are additional problems in the non-co-compact case. Yeah, but I mean, you're completely right. There's this paper by Wogan, and there's also other work about vanishing in a lot of cases. And so it seems, so this goes exactly in the right direction. But I don't think that the general result, at least for the lattice case, is not in the literature, but it's probably true. So, I mean, it's natural. So, so if you have this SLN, Z, is it n minus 2 Kashdan, right? That's a natural question, right? And n minus 2 is the natural generalization of 2 Kashdan. But that is not true, because there is some stable homology that arises as n tending to infinity that's related to the algebraic K-theory of the integers. And it's coming already from the trivial representation. So I guess if you want a positive result in general, you would probably have to exclude maybe finite dimensional representations and their cohomology, something like this. And then maybe there's even a more general result that really up to the rank minus 2 in some suitable sense, it has a vanishing of a cohomology with unitary coefficients. But that's just a conjecture or just a guess. But I think there's some indication that this could be true. So let me first finish the proof before I go to the next slide. So why has this proven the corollary? Well, we have a construction of a non-residually finite central extension of some p-adic lattice, and we prove that those are 2 Kashdan, right? So there was previous work showing just studying these p-adic groups in higher rank and proving that they are 2 Kashdan by Ballmann and, sorry, now I forgot.
Swiatkowski, something like that.
Yeah, Swiatkowski, Ballmann, Swiatkowski, exactly. So my colleague from Krakow, Ballmann, Swiatkowski. Sorry, I forgot his name.
But,
okay,
but
so
you must mention Garland, because all is
exactly.
really going back to the fundamental work
Right.
of Garland. And let me just mention that next week is our open. We'll talk in this seminar.
Exactly.
It will be a kind of a crash course in on the Garland theory.
Right. Okay, and so this is also why I will not go into the construction of, or in the proof of this property that these are 2 Kashdan, right? This is a different story. We had a hard time proving that certain finite central extensions of it still have the 2 Kashdan property and are at the same time non-residually finite, right? So this was where we extended the Linnaeus ideas, and we used a lot of input on algebraic groups to extend it to this p-adic lattices. So the Linear, he proved that certain central extensions of a lattice in the symplectic group is not residually finite, even though it's a finite central extension. So that was very surprising, and we translated this into the p-adic setting. So this was another part in our paper in order to provide a suitable example that has all the properties. So what the rest of the time I will spend on explaining how this theorem is proven. So what's the relationship between vanishing of the second cohomology and the stability with respect to this Frobenius norm? So let me say something about the idea of the proof. So I have to introduce some notation for it. So first of all, this is our finitely presented group. We have just a map on the generators. We find these unitaries. So this is just has a unique extension to a homomorphism on the free group. And we define what we call the defect to be the maximum over the finite set of relations of the distance of phi of r to the identity matrix. So if the defect is equal to 0, then it's actually a homomorphism on gamma. And if the defect is epsilon, then it's an epsilon homomorphism. So now suppose we have a sequence of such maps, or such tuples given on the generators, so that the defect is tending to 0, right? So this exactly means that you have a sequence of epsilon homomorphisms where epsilon tends to 0, right? So that's the situation that we study. And what we have to prove is that actually this is close to a sequence of true homomorphisms, right? This is what exactly stability would mean. And we translate this into a cohomological problem as follows. So we define C of G comma H to be given in this precise form. So it's phi n G, phi n H minus phi n of GH divided by the defect. So since we are dividing by the defect, we turn this into a sequence, right? So this is a sequence, it's indexed by n, which is like normalized to be of constant size, right? Dividing by the defect is exactly dividing by the mistake by the difference of phi n G, phi n H to phi n GH. So we are renormalizing it to be basically of constant size, depending on n, right? So the size will depend on G and H, of course, but it's in the n direction, it will be normalized so that it's bounded by a constant. And now it's essentially already given as a boundary, and so this will define a 2 cocycle on the group gamma with values in this strange metric ultra product of matrix algebras that we have. Well, I talked about the metric ultra product of unitary groups, but the metric ultra product of matrix algebras, it's just the Banach space ultra product of these algebras. And in case of the Frobenius norm, now something very nice happens. This ultra product is again a Hilbert space. So it's a standard fact that an ultra product of Hilbert spaces is again a Hilbert space, basically because the parallelogram identity still holds in the limit. So it's still a Hilbert space. And we can now consider the second cohomology of the group with coefficients in, well, in this crazy ultra product Hilbert space, where all the epsilons have tend to 0. So you're actually acting with your group. So it's a unitary representation of the group. And you have a 2 cocycle. And now somehow the algebra just does some magic for you, because if you can write your C now as the boundary of a 1 chain or 1 cochain, then this 1 cochain, it exactly tells you in which direction you have to correct your almost homomorphism, right? So this is this phi. It exactly gives you the right direction in which you have to correct it, so that this new corrected sequence, psi n, is still close. I mean, that's easy to see because you made a correction of the order given by the defect. So it's close as small as the defect was. But the magic is that the defect of psi n is now little o of the defect of phi n, because you have just corrected it in the right direction, so that the defects or the problems the problems kind of cancel out. The first order expressions, they just cancel out, so that the defect of psi n is really tending to 0 smaller than the defect of phi n. So I think maybe this is convincing, but of course you need to check all these computations. And the only thing I can tell you is that submultiplicativity of the norm is used heavily in these computations, and we have been trying very hard to get rid of it, but this was not possible, right? So this proof, therefore, does not work for the normalized Hilbert-Schmidt norm as you would like it to do. If you want to study con-embeddable groups, you need to study the normalized Hilbert-Schmidt metric. It just works for the Frobenius metric, because at the same time, it's a Hilbert space and it is a Banach algebra, right? So these two properties together make the proof work, right? And we don't know how to make the proof work.
Yes, let me say one sentence. Let me say one sentence for the loyal participants of our seminar. I think we saw it in one of the lectures, but I'm not completely sure. But anyway, it explained very nicely in the paper of Gulnara and Pliviu that stability is really a question about lifting from the topological ultra product of the groups UN or SN to the direct product. Like
Right.
you get an orphism, it's a question of lifting. And this is a kind of an hint that H2 is relevant, because all this looks like a magic, why H2 is relevant to the problem. If the norm is submultiplicative, you can approximate that lifting problem by a billion lifting problem. But in principle, the same lifting problem exists also for the normalized Hilbert-Schmidt norm. It's just that we don't know to approximate it. If somebody can develop a non-commutative cohomology, H2 non-commutative, then
it's nice to see you so excited that you want to give my talk, Alex.
I thought you said you're finishing. I'm sorry.
No, I still have a few minutes, but this is.
Okay. Sorry. Yeah. No. Go ahead, please. Sorry, I'm sorry.
No, I think this is exactly this is the nice. I mean, you are completely right. I mean, I don't need to repeat it because you said it exactly.
No. Repeat.
Right
Say it, please. I mean, I think that would be good for people to say again. I just didn't want them to think.
I mean,
that we are such magicians.
Let's first finish the proof, and then I will make some further remarks.
I'm sorry. Yeah, thank you.
Because what did we prove now? Well, we didn't prove that phi n was close to a homomorphism. We were just proving that it is close to some sequence that is less bad than epsilon homomorphism, right? So it has the defect is decaying faster, right? And so there are various ways to finish the proof. Either you can repeat that process so that you converge to an actual homomorphism, but that's sort of also technical. But you can also finish the proof by some contradiction type of argument where you assume that phi n was in a suitable sense best possible epsilon homomorphism, which is not improvable in some sense, right? And then you run into a contradiction, right? So that's the end of the proof. And exactly as Alex said, it's in the end, it's the problem of splitting an extension. And that's why it was not, I mean, that was basically also the reason why we started looking at second homology. But it's really true that if you have this ultra product of unitary groups, it is the image of the product of unitary groups. And then there is this kernel, this group NW, right? And a priori, your group gamma, it maps here, but you wanted to lift the homomorphism to the product, right? That's the stability problem. And so it is some non-abelian second cohomology problem a priori with coefficients in here. Right. And what the submultiplicativity does for you is really to slice this problem into an like infinite number of a billion lifting problems, And the reason for this abelianness is in some sense the fact that the commutator of two elements is close to the identity in a way which is quadratic in the inputs, right? So maybe there's a factor 2 here or something like this. So this is the reason why commutators converge to the identity faster than individual elements. So if U was converging like epsilon and this also like epsilon, then this would converge like epsilon squared to the identity. So if you have a sequence that converges at a certain rate, and you take a space of such sequences, let's say, and you mod out the sequences that converge at the quadratic rate, then that quotient by the sequences that converge quadratically fast is an abelian group, just because the commutators of two arbitrary elements are in this subgroup of those sequences that converge twice as fast, right? And so that's basically the reason why we can reduce it to an abelian problem, and it's really to make it at the same time a Hilbert space problem that kind of needs some tricky arguments, but that's exactly what we did. So I want to thank you for your attention, and I'm finished with that.
Wow, thank you very much. This was great. Are there further questions? We disturbed you quite a bit, but I'm sure Andreas will be happy to take more questions if somebody wants to ask. If you want to ask, please don't. I cannot see you guys, so please just talk if somebody wants to ask something.
Can you now maybe go back to this computer science theorem and the relation to this cons embedding problem? And you added that some variants on it, some may be true, some may be false. Could you clarify that a little bit?
So the con embedding problem, the way Con stated it, was for 2-1 factors. So these are particular types of finite von Neumann algebras. And the most important examples in some sense are group von Neumann algebras. And so if you would know a positive answer to the Con embedding conjecture for a group von Neumann algebra, that exactly means that this group is Con embeddable. Okay. So that covers a large class of von Neumann algebras. Now this computer science approach is taking a completely different angle. The sources of examples are coming from quantum games and like sophisticated ways of quantum information theory usage in information science and game theory. And so they come up with a completely different set or source of examples, and in one of those examples they can prove that it's not Con embeddable, but it doesn't give you a concrete group which is not Con embeddable.
So there's a problem of Con about this embeddability, which is about von Neumann algebras, which does not necessarily come from groups. And yes, it's that they find counterexamples.
Exactly.
Okay. And since we all group theorists, we're not so
exactly.
Okay. Okay. Thank you. Very nice talk, by the way.
Thanks.
Any more questions?
I wanted to ask, so you gave examples of Frobenius stable groups, but I mean, somehow the Frobenius norm is kind of similar to the operator norm, at least in questions of stability, I guess. Are there examples of differentiating operator norm stability and Frobenius norm stability to you?
I'm not aware of examples like that. No, this is very complicated. I mean, so
no, actually, I don't know. I know.
Really?
I know, and it will come up in the second semester. I am now talking, is Shmuel still online? With Shmuel Weinberger about that. There are examples of groups which are Frobenius stable, but are not operator norm stable. In fact, for operator norm stable, if you know that H2 does not vanish in the trivial module, then you can deduce that it's not operator stable. We don't have such if and only if theorem like that. Let me make it clear. But this relates to almost flat bundles and things like that. So if you take co-compact, and moreover, it's enough that H2i of the trivial module will be non-zero for some even dimensional cohomology in order to deduce a non-operator stable. So take example of the type of Garland with lattices in an even dimensional Brouwer-Titz buildings, then everything vanished in the lower cohomology, including H2, which means that they are Frobenius stable as we know. On the other hand, they are not operator stable.
So that is maybe related to this work of Mario Stadlerlat?
Exactly. That's it really goes back to Gromov, Kohns, and Muskovsky, and Daralat now gave a more general relate. Exactly. You're completely right, Andreas. That's exactly that.
I see.
And Daralat will talk also in the seminar next semester. So keep tuned. It's going to be interesting.